copying nature with a view to using it in engineering. And you'll see other examples of that in the middle of the picture. You'll see the gecko, which is a famous one because by copying the gecko's brilliant system on its feet, where it's got tiny little hairs, it's able to climb up walls and even walk on roofs without any problem, walk upside down basically. There are a whole host of possible areas where biomimetics comes in. If you look at the top left, there is the lotus leaf, which means that water rolls off a lotus leaf because of the tiny little hairs which make the leaf hydrophobic. That is, the leaf doesn't want to collect water because of the hairs. So it tends to roll off the leaf, and the idea of self-cleaning glass came from that idea, which has actually gone into some industrial applications. And there's many other examples. Now, as was mentioned in the introduction, Richard Dawkins actually got wind of the fact that myself and Stuart Burgess, my colleague, who wrote this book, by the way, two copies are there, he got the wind that we were working on ideas from nature and our belief in design, and he said, if Burgess and McIntosh, or maybe Burgess and McIntosh are right, and all the rest of us, biologists, geologists, archaeologists, historians, chemists, physicists, and so on, yes, thermodynamicists and respectable theologians, the vast majority of Nobel Prize winners, fellows of the Royal Society, and of the National Academies of the world are wrong. And then he said, not just slightly wrong, but catastrophically, appallingly, devastatingly wrong. It is possible. If Burgess and McIntosh are right, the scientific establishment has fallen. What a wonderful statement. Well, in the teeth of that stuff, I just carried on and actually looked very carefully at the Bombardier Beetle. With others, of course, this is not just my work. I owe much to those who know a lot about engineering, and Tom Eisner, who's died now, but who knows a huge amount about biology. So I looked at the Bombardier Beetle, which is found in Asia, in North America, South America, Africa, and other places. This is the African one, found in Europe, south of England, usually under rocks close to water. The Bombardier Beetle ejects a mixture of chemically heated steam and noxious chemicals out of its back end. This is a separate system to its digestive tract. This wards off predators such as ants, spiders, birds and frogs. And the beetle generally wins and stuns its opponent. Amazingly, it's got a movable exhaust turret at the back, and it can swivel that turret in any direction it wishes, even over its head, which is what you saw on one of the leading pictures as we were looking at the first slide. If I was to get a tank, right, and able to move that turret, I could do this with the turret and move it round, push it up a bit, but I wouldn't be able to bend it right over such that it pointed the other way. Nobody's copied that turret yet, but we have copied the amazing valve system which is in the Beetle. These are the initial pictures that Tom Eisner from Cornell University in upstate New York near the Finger Lakes. This is some pictures that he took and published in 1999. They were inspirational to many people. And as a result of his work, I realized, this is in his laboratory, what was going on. That's the noise you actually hear if you had been in the laboratory looking at the African Bombardier Beetle that Tom Eisner and others had. This is another film of the Bombardier Beetle. This is from the film Alien Empire, published by the BBC some years ago.
Few creatures will risk annoying a Bombardier Beetle. It mixes a cocktail of deadly chemicals in a special chamber. They react and explode at boiling point from its rear end in an awesome chemical weapon.
That was pretty impressive, I think you'll agree. But even more impressive is when you actually play things a little bit more slowly, which is what we're going to do now. This is a set of 2 video clips from the film Secret Weapons, published again by the BBC of Tom Eisner's work.
One of the really amazing things about this animal is its ability to spray in a very beautifully aimed fashion. And that shows up very nicely when you put the animal on indicator paper. And what I'm going to do now is I'm going to pinch very lightly one leg after the other, just as if I were an ant biting these legs. I'm going to start with the right hind leg, right front leg, left front leg.
Quite extraordinary, I think you'll agree. Now we're playing it more slowly.
At 400 frames per second, the action has been slowed down, but not enough to see the individual pulses. So they went to a lab and filmed the Beetle at an even faster speed, at an incredible 4,000 frames a second. There were the pulses, each one corresponding to the individual bursts of sound.
Now remember that 4,000 frames per second. I could see that it was roughly about 10 frames per blast, which means that, as in fact others have already found out, the notes that you hear from the Bombardier Beetle in Tom Eisner and other people's laboratory is it's a pure note, you understand? If you've got a pure note, that means that there is one particular frequency that it's vibrating at. And of course it is around 400, perhaps up to 500 times per second. So the Bombardier Beetle, others have found, is basically doing a series of explosions. And it's really what we would call in the combustion community pulse combustion par excellence. There is really 4 stages, well, 3 primary, but then there is a 4th as well. There is a stage where the liquid mixture is coming in, which is a combination of hydroquinone and hydrogen peroxide. If you know anything about hydrogen peroxide, if you've got pure hydrogen peroxide, it just oxidizes everything in sight, including you, if you're not careful. So pure hydrogen peroxide you have to be extremely careful with. Well, this beetle has got a low dilute mixture of hydrogen peroxide, and it's got hydroquinone, which is like a hydrocarbon fuel that you would use in petrol, but you don't use the word petrol, you use gasoline. Why? Change the language, but anyway, once then there is ignition, and the ignition I'm coming to in a moment, then the door through which, or the valve through which that stuff came in, says, okay, I need to close the doors because the pressure is going up in the combustion chamber. And by the way, this is only about 1 millimeter long, so it's absolutely tiny. Then, of course, once the explosion has gone out, then there is a low frequency part of the cycle, and then the doors will open again and more fuel will come in. So, depending how you measure it, there really is essentially 3, if not 4, stages. And a German scientist called Schildknecht actually worked out what the chemicals were in the Bombardier Beetle. There is an interesting sub-story to this, because Schildknecht was a Nazi during the war in Germany. Eisner, as you probably realize by his name, was a Jew. He's died now. And he told me all sorts of tales about his father having to come out of Germany and eventually they ended up being in South America. And it's a sort of an interesting twist in this story, because you'll see another connection with the Second World War a little bit later. So what really became evident, and this was really so exciting for me, was that there was an exhaust valve which we only discovered a bit later. Even Tom Eisner and others hadn't talked about an exhaust valve. We knew that there was an inlet valve, but it only became later evident that there was an exhaust valve as well. I said it would be a long time later that I'll tell you about the Second World War connection, but here it is. I put it in earlier. This noise you won't recognise because you don't come from the country which was being attacked by V1s or doodlebugs. I don't remember it either because I was alive then. But this noise is the noise of the V1, which was powered by a series of explosions just like the Bombardier Beetle. When it stopped, the warhead came down, and the bombs fell on London and all the surrounding district. But what's interesting is that, as I've just mentioned, it was powered in exactly the same way as the Bombardier Beetle. And indeed, the Bombardier Beetle braces itself, because if it doesn't hold itself firmly, it would be propelled forward by the blast that's coming out of its backside. Well, it's not really its backside, it's a separate track dimension. So it's not doing a, it's not doing a little thing that perhaps you might say is a bit embarrassing. It's actually not doing that at all. It's coming from a completely different opening. But so the whole thing is it's quite fun to think about what's going on. And of course, doodlebugs, the people who invented the doodlebugs, it wasn't von Braun, he invented the V2. It was another German scientist who invented the V1. But my point is this, they didn't know anything about Bombardier Beetles. It's interesting. They may even have thought that they were inventing pulse combustion. But pulse combustion was already in nature and was in these little Bombardier Beetles, only to be discovered many years later. So it's a series of explosions. So that is why it's called the Bombardier Beetle. It's a bombardier, right? With a gun, with a cannon. And I've just simulated what is going on. Now, let's come a bit more to the chemistry, because a certain Richard Dawkins, whom I mentioned earlier, had a few comments about the Bombardier Beetle quite a few decades ago. So we'll introduce the chemistry. The chemistry, and I'm sure you all know about advanced chemistry, don't you? Well, I'll guide you through it. You'll see on the left there that there is, and I'm sure you all know it already, that this is the formula for hydroquinone and hydrogen peroxide. Actually, most of you probably would recognise that. And it produces benzoquinone and steam or water. Now, having got that going, you will probably realise, some of you, that that doesn't easily, only a few of you will realise this, that reaction doesn't easily take place. It needs a catalyst. You've heard of catalytic converters, which are used to clean up the exhaust of cars. Well, again, that's a catalyst. It doesn't take part in the actual reaction, but it encourages the real reaction to get going. So the enzymes, or the catalysts, are called catalase and peroxidase. Now, we'll listen to Professor Dawkins. Not recently, this goes back many, many years. In fact, it's going back almost 30 years. So you'll see a young Richard Dawkins giving the Christmas lectures to students and pupils, basically children really, at the Royal Institution lectures, which take place every year in London. And this is what he said.
In fact, the hydroquinone does nothing at all. We can put that on one side. The true story is that hydrogen peroxide on its own does decompose to form oxygen and water, but it needs a catalyst under normal conditions to do that. This black powder here is a catalyst. It's not the catalyst that the Bombardier Beetle uses. The Bombardier Beetle does use a catalyst, and it does in fact squirt this hot substance into the face of its enemy. But if you put a catalyst into a weak solution of hydrogen peroxide, then you're going to get a little bit of bubbling, and it's a little bit warm. That might have some effect on a predator, that might slightly deter a predator, and it would be not particularly dangerous to the beetle. Now we've got a smooth gradient, a bit more concentration of hydrogen peroxide, and that's distinctly warm. That would work more effectively against a predator. And by moving gradually up the slope, gradually increasing the concentration of hydrogen peroxide, we can end up with... So there is a smooth slope all the way up to the effective deterrent against a predator.
Let me just explain. He, with his atheistic philosophy, is trying to say that there is a natural progression which would just sort of gradually happen over a long period of time, and eventually you will get the sophisticated chemical system in the Bombardier Beetle. He actually missed a crucial step. I'll come to it. The chemical reactions within the Bombardier Beetle are now what I'm going to address. Please note, I have not copied the chemical reactions of the Bombardier Beetle, but we do understand, in a measure, there are still many things to be found out. We understand in a large measure what's going on in the Bombardier Beetle. It's taken many decades with a number of people, Schildknecht I mentioned, who was a Nazi sympathiser in the Second World War, Tom Eisner, whom I owe a huge amount to at Cornell University, and I really do hold him in high regard and his memory. He wrote the book For the Love of Insects. So I'm standing on giants, right? I'm nothing. I'm just standing on other people who've actually looked at this work, or looked at this beetle. But we've gradually understood what's going on, that many other people have worked on the Bombardier Beetle as well. And what we found is that there are catalysts. Tom Eisner was of the view, it's not quite been proven yet, that within the combustion chamber, and this is the 1 millimeter combustion chamber, blown right up, okay, there's lots and lots of what look like threads coming in from the combustion wall. And we think that those fibres are carrying catalase and peroxidase in crystalline form. There is a lot more to the Bombardier Beetle. It's the tube feeding in those chemicals, which also may be highly relevant. Now I want to show you a very important experiment.
Drop it straight down the center.
This is at Liberty University.
Yeah.
This is Garth Hewitt at Pittsburgh.
That was a platinum catalyst.
Platinum catalyst.
And now it's your quinones form. See, that's orange?
Yes, that's the orange. Thank you for showing me this, Garth. This is excellent.
Yeah, that orange there would be your benzoquinone. Wow, what you trouble.
Now, the significance of what I've just shown, I want to explain. He is showing that when you've got not just hydrogen peroxide, which is all that Richard Dawkins was showing you, but when you've got the hydroquinone in there as well, things go in a sea change in terms of the amount of heat and the amount of huge effect of the catalyst. And I'll tell you for why. Of course you know all this, don't you? Because you know advanced chemistry. But let me just explain it to you. Actually, of course, most of us don't. And I had to learn quite a lot as I did this work myself. If you see a plus sign here, it means that you've got to put energy into that reaction. Do you understand me? Okay? Some of you will know this already. If you see a negative sign, that means that that particular reaction is giving out energy. Don't ask me why it's that way around, that's just a convention. Okay? We won't worry about that. So look at this. What about this one? This is a negative sign, so that means it is giving out heat, so you've got the point. And this is hydrogen and oxygen going to water. You all know that hydrogen is a very dangerous gas. If you fill a balloon with hydrogen, okay, yeah, that can act as an airship, like the R101 did years ago in my country. But as soon as it ignites, bang, you've lost the lot, and it's highly dangerous. So why am I putting up? Well, we know that there are a huge number of reactions going on, but the reaction which is most important is this one. Now, why do I highlight this? Because a certain Richard Dawkins missed the importance of this reaction. You heard him actually say, oh, we don't need to worry about the quinone. But the quinone is vital, because the quinone, even though it takes a bit of energy out, okay, it releases, hydrogen. And it's the hydrogen combining with the oxygen as well as this reaction, which then really causes a runaway and an explosion. I would suggest to you, I'm not going to say I know, but I would suggest to you that Professor Richard Dawkins was not properly understanding the importance of thermal runaway reactions. Basically, you've got to liberate the hydrogen. Yes, of course, we know that the peroxide is the thing which you've got to get going, and the catalyst breaks this bond and enables hydrogen to be released. Once the hydrogen is released, then this is the reaction which is the most important. So overall, when you add these figures up, overall it's less than that obviously, but you get minus 203 joules per mole for the amount of heat coming out. And by the way, it's not very simple to produce hydrogen peroxide. It is believed, again Tom Eisner was the one who gave his view here, it is believed, but it's not been proved, that the tubes leading to this combustion chamber actually carry the hydroquinone and the hydrogen peroxide together. Now, why is that of interest? Well, because actually when you think about it, if there isn't a catalyst, these things won't react. And it's only when they get to the combustion chamber that the catalyst is there. So, amazingly, the Beetle has a way of producing hydrogen peroxide on tap. We've not yet managed to work out how that happens. Maybe somebody in the future, and I hope we can inspire some of the young people here to go into this system and to see whether you in your life's work can solve how the Bombardier Beetle, finally, it can be solved, how it produces hydrogen peroxide. Let's just consider those combustion chambers again. You might regard them as carburetors. So you might say that this Beetle has a twin carburetor system, rather like a motorbike. And you're going to see now that it's got some incredible system of valves, and this bit we have copied. It's a bit like a boxing glove. And as the pressure goes up, the tubes which carry all the chemicals coming in are pinched, and that is the inlet valve. So these pinch the inlet tubes under pressure. When you actually look at this diagram, this is really a light bulb moment. We, together, Tom Eisner and myself, realised that there was an exhaust valve as well. I asked him, what's this? Have you just cut through the exhaust tube? He said, no, I haven't. That is the exhaust tube. You're looking at it from the outside. So I said, what's this membrane here? He said, it's a membrane which lies flat generally, but presumably lifts up under pressure. In other words, it's what we call a balloon valve or an exhaust valve. It actually opens under pressure. That was a crucial moment when we discovered that the valve opens under pressure. When you look end on at that outlet valve, the membrane is lying on the hard cuticle, right? But then under pressure, it opens. And I must acknowledge here Christine Ortiz from Massachusetts Institute of Technology, who, using laser tomography, has shown that both combustion chambers usually operate together. As I said, twin carburetors going on. So watch this, okay? You can actually see I'll just see it again, you can actually see the exhaust system going on of both combustion chambers. She did very well to produce that, and I'm grateful to Christine's work. So the insect of the Bombardier Beetle, and this classic picture is showing it moving over, the little tube moving over its front and attacking the finger, which it thinks is a frog or some other creature wants to eat it. This system we've mimicked. Please though note, we have not mimicked the chemistry. We just mimicked the valve system, coupled with electrical heating of the little chamber, which is nowhere near down to 1 millimeter. We've got a chamber that I'm going to show you roughly of about 2 centimeters. And you'll see here that this is a computer generated diagram and it's part of a cylinder. So it's about 1/8 of the area going around the cylinder. And we're mimicking or copying or simulating the tube coming out of that chamber. Without going into too much detail here, there are some assumptions. Some of you here, 1 or 2 of you, may know that you've got to work out whether you've got laminar or turbulent flow. We won't go into detail on this, but I'll just say that we assume laminar flow. If you don't understand that, there's no need to worry too much. But you do have to make some assumptions about what type of flow you've got. And it's a 2-phase flow. You're dealing with air, primarily, and water. The air is out here, and you've got water in there. But when the water boils, you've got steam. So actually what we did is we just said, okay, the air is obviously going to not really play much of a part once you get going. So we'll just use steam and water, because the steam is going to be generated in here. Once this valve opens, and we decide when we're going to open it, we also decide what pressure we're going to use. And we're going to suggest, we don't actually know what the pressure is in the Beetle because nobody's put a little diagnostic little cup, some pressure transducer in such a tiny little critter. It would be very difficult. So we don't actually know what the pressure is, but we suggest about 1/10 of a bar, which is quite large actually. Speech actually uses, it's really a thousandth, 10 thousandths of a bar, basically, of a Newton per meter squared, which itself is 100 thousandths of the pressure in this room. So it's actually a very, very large pressure if you have 1/10 of a bar. But to get the effects that we're going to now show you, we do believe that there is quite considerable pressure in there. So we've estimated 1/10 of a bar, which is about 10,000 pascals. Just momentarily, it's not, if you held that for a long time, it would blow the Beetle to bits. But just momentarily, it could go up as high as that. It may be less, but we're just suggesting that. So we let go, and we find out what happens. As I say, we assume laminar flow. So this, you're going to see in a moment when I set the clock going, that this is going to give the impression that you're going back in. That's just an illusion, because what's happening is more and more red and brown, which simulates the steam, is actually taking place, right? And the important thing is to watch what happens up here. You'll see the clock going. And as the milliseconds go by, we want to make sure that we get most of the water, most of the steam out of this cylinder. So let's set it going. And we're going in steps of 0.06 of a millisecond. So you can see the clock up there. You've got this impression of going back in, but actually it's coming out that way. The blue is the cold, this is slightly warmer, and this is hot here, so it's mainly steam. Okay, so it's a mixture of steam and water, which now, as you see, we've got to 2 milliseconds, so that's equivalent to 500 cycles per second. If we go up to 3 milliseconds, then it's about 300. And you can see that by 3 milliseconds, most of the steam and the water has come out. So we knew that it was something like that that probably was going on in the Bombardier Beetle. We did try without a pressure release valve, and it took an awful lot longer for the boiling water and steam to come out. It's a bit like a pressure cooker. Have any of you seen your grandparents use pressure cookers? We don't use them these days because we have microwaves. But you know, you used to have a weight on the cooker to make sure that more water and steam would make the cooking go much faster. These days, as I say, we use microwaves. So, some very benevolent Swedish donor actually said he would sponsor the building of a rig simulating the Bombardier Beetle. So we built a rig which was approximately 20 times, as I say, the size of the combustion chamber. So we're making that about 2 centimetres. I did tell you something not quite right earlier. The Bombardier Beetle chamber is 1 millimetre, and I did tell you something incorrect there. When I was simulating this Beetle chamber, right, we were still keeping the distance as 1 millimetre. We weren't simulating our experiment. So when we came to actually doing our experiment, we were going up, as I say, to 2 centimetres, and initially we had a perspex combustion chamber. We had a heater inside electrically. We wanted to see what was going on, so we actually had to have it transparent. In the end, we abandoned that, but we have the exhaust nozzle coming in there. This is the inlet valve here, so that's the exhaust valve. We control the exhaust valve, there's no chemistry going on, and we also have a second relief valve here, just in case something goes wrong, because you're dealing with steam. Now steam, if you know, like for like in terms of mass, steam occupies something like 1,600 times the volume of liquid water, mass for mass, okay? So if you've got a gram of water, it will occupy a certain volume. It will be 1,600 times that for the steam. So it really is a very powerful system when you get what's called a vapor explosion. So when we got this system working, it was really a day of rejoicing, because we had actually simulated what the Beetle was doing. And this is an early experiment. And I think you all agree with me that that's a very sophisticated receptacle that we've got there for collecting the water, right? We won't go into the detail, but we had to get lots of systems there to make sure that we were not spreading water all over the laboratory. This actually is quite a sophisticated piece of equipment. It measures the droplet sizes, which is actually quite important because we want to use this for industry. So we haven't quite perfected it then. That was one of the very early experiments which I took on my photo, on my camera, on my phone, in order to record it. Now let's just summarise the things that we know about the Bombardier Beetle. It has a sophisticated inlet and exhaust valve. It makes a mixture of water and steam under pressure. It's mixed with steam and water. Steam and water is mixed with a noxious quinone. The heating is by a chemical reaction, which we've not copied. It can direct the blast in any direction it wishes. It can blast at 400 to 500 times per second. Then it can also maintain that blast for 2 or 3 seconds, then stop. Then do it again, and then stop. Then do it again, probably about 10 to 15 times, before it begins to run out and get exhausted. That is pretty sophisticated, I think you'll agree. It is also an example of pulsing combustion. It is a classic example of biomimetics copying nature with a view to using it in engineering. The core technology copied is the combustion chamber, valves, and the nozzle. There are applications to nebulizers in pharmaceuticals, which for people who are having difficulty taking drugs. We're at this time developing a project based at Liberty University. We have lab space, but we don't yet have the financial support to build a prototype fire extinguisher where it would be entirely water and steam, of course, which we think could be very useful for fighting wildfires such as have recently been seen in California the last few years. And of course it can also be used for aerosols and air fresheners maybe somebody would find it rather fun to have a Beetle-inspired air freshener in the corner. We'll see. Just one last thing that I'd just like to show you, and that's from the BBC Live series, where David Attenborough comments on the Bombardier Beetle and the distance that it can throw. Now, I've put there a throw ratio of 200. What do I mean by that? Well, the distance it can throw is 20 centimetres, right? Divided by 1 millimetre on this on this Monday evening. What does that come to? 200, right? 1 millimetre into 20 centimetres. And so that is interesting, that throw ratio. Remember that throw ratio, because that's going to be pertinent to yet one more point I'm going to make about what we're doing.
But the master of chemical warfare is the Bombardier Beetle. It can create a chemical reaction within its body so violent that boiling caustic liquid explodes out of its abdomen. By pulsing the jet 500 times a second, it keeps its rear end just cool enough to prevent it being cooked.
That is really quite remarkable. And the ant is recovering, and the beetle just walks off. That is often, of course, what happens. The beetle generally wins. David Attenborough made this comment that it might stop it cooking itself by doing it at 500 times per second. Actually, that's not the way it stops itself from cooking itself. It's got specially designed chamber where the material properties of that chamber stop heat transfer, low conductivity, heat conductivity. Low heat transfer means that it doesn't start heating the rest of its body and burning it. So he's not quite right that it's connected with the 500 times per second. But the distance it throws is phenomenal. A throw ratio of 200. Well, if we've got a chamber which we got of 2 centimetres in these early experiments, then 2 centimetres times 400 on a Monday evening, can you do the sums? Comes to 4 metres. And that's exactly the sort of level we got. Okay, it does depend on how large the droplets are and many other things going on. But we certainly know that we can reach the same throw ratio from 2 centimetres. If we go further and go to 4 centimetres, then we should be able to go up to 8 metres. 8 metres, for you who perhaps would prefer to use feet, and I don't blame you actually, I still use feet, right, is 24 feet, right? So I'm saying between 24 and maybe even 30 feet might be possible. If you're fighting a wildfire, right? If you're constantly having to drag hoses heavy with a huge amount of cold water, you can probably do the same thing with a much smaller amount of water because you're primarily ejecting steam. So you've got the possibility of carrying a small amount of water on your back. It means the firefighter's more mobile. He can also do things more remotely by shooting steam into the seat of the fire. It's yet to be proven, and it's only an idea at the moment, but we're seeking to build a laboratory to do that. Then there are other applications. Fuel injectors is a major one, which is already being used by the company which is developing this work. Actually, it's injectors of additives that are going on, but nevertheless, it's a very good application of the Beetle. In this case, the gasoline, which you would call, the proper word, of course, is petrol, but maybe slightly twisted the language. But let me just say that there are major patents for these applications. Fuel injector, fire extinguisher, pharmaceutical spray system. What was said by one of the patent agents, you would call them patent attorneys, advising our projects, it was, maybe we should try and patent the Beetle. But as was said in the introduction, I think the Beetle design as a whole is already patented. That is, there is a design in the whole system which would be very difficult to say we originated it. We, of course, didn't. We just copied certain aspects of the design. Later rigs that we have built are actually now getting up the frequency to a much higher frequency, and we're also able to control the system a lot more. Here's some videos of this these later rigs. Speed is going up to 100 times per second, even 200 times per second, which can be exceedingly useful for fuel injectors and indeed could be very relevant to fire extinguishers. Wouldn't so much be needed to use for fragrances. You wouldn't be wanted to get water all over your living room with that sort of spray, but you can see the general application in these later rig systems. So the applications for the Beetle technology, which I've already mentioned, from the physics of the valve system, right, are all based on a number of things which can be changed in the system that we've now made. Inlet valve timing, pressure relief, exit valve, the temperature of the chamber, repetitive pulses and so on, modality, which means what sort of size of droplets, do we have two sizes together, all these sorts of things can be copied, and it has applications to pharmaceuticals, needleless injectors, fire extinguishers, fuel injectors, aerosols, aeroponics even. I won't go into the explanation of aeroponics at this moment, but that's just a system for growing plants when you don't have gravity, maybe in outer space, which may become an issue if you go to Mars. Then you may need to grow your own vegetables, right? That's the sort of thing we mean by aeroponics. And there could be a relevance to that, but people haven't yet applied it to that system. But the three main ones are the top ones: nebulizers, pharmaceutical applications, fire extinguishers, fuel injectors. Then there is another application that I've mentioned to aerosols, but that hasn't yet taken off either. Just to say that the droplet sizes here in microns, which means you've got 1,000th of a millimetre, which means you've got a millionth of a metre, so you've got this little symbol mu. You've got about 1 to 10 microns for the pharmaceutical, about 100 microns, which is bigger droplets for a fire extinguisher. Fuel injector, you're dealing there with gasoline, petrol, as I say, for an engine, it would be about 10 to 50. Aerosols would be just a little bit less than that. So this is featured on many programs. The One Show some years ago did a presentation of this work where Mike Dilger actually presented my work. Also, this has gone around the world, not only in England, BBC Look North, but the Discovery Channel did this some years ago, did a presentation on the Bombardier Beetle. BBC Material World, the German Der Spiegel, and a number of other publications have actually done a little bit on this. Even Scientific American actually produced something on this work. So I remind you that the design features of this Bombardier Beetle are really extremely interesting, and they show that you are not dealing here with something simple. It wasn't a matter of gradually climbing the mountain, as Richard Dawkins suggested in one of his books, Climbing Mount Improbable. That gradually, as he tried to show in 1991 in the Christmas lectures, you could gradually evolve this system. Frankly, all the evidence points in the other direction. Do you remember I said at the beginning, Richard Dawkins said, well, McIntosh and Burgess, not just slightly wrong, but catastrophically, appallingly, devastatingly wrong. It is possible. So he did admit that. If Burgess and McIntosh are right, the scientific establishment has fallen. He loves to make such dramatic statements. Actually, I didn't have the last word. Maybe the one whom I serve had the last word. Because I am a Christian and I believe in design. And I believe this is consistent with what the Bible actually says. In 2010, the Times Higher Educational establishment, which really is part of the newspaper consortium, and it's just called the Times Higher Ed for short. They produce awards each year, and it was to the University of Leeds, which I was at, and also to Swedish Biomimetics 3000, which sponsored this work. And they gave an award for an outstanding contribution to innovation and technology. May I say, the glory is not to me. All I did was ask the right questions. And may I say, the reason I asked the right questions is significant. Because I was open to a design thesis for this Bombardier Beetle. Those who say that if you believe in intelligent design, it closes down research, totally wrong. If you believe in an intelligent design position, you will ask questions. Why? Or indeed, how does this work? Many years ago, in a book which is probably the first written book that we've got, do you know what that book is? It's the book of Job. And in it is written these words: ask the beasts, and they will teach you. I would suggest to you that if you ask the right questions, you'll get progress in research. In other words, I was asking the question, there is something going on in this beetle which is making it able to spray not just any sort of bit of dribble of droplets at steam. It actually shoots them. Now that requires power, and I knew full well that there has got to be some way of building up a pressure and bang, out it comes. We did know it was a series of explosions. Tom Eisenhower showed that. But even he, though he wasn't coming from a similar perspective to me, and I'm not saying that, but I am saying that it's important to ask the right questions, and he was asking the right questions. He was saying, how does this thing work? Now, if you believe that something's evolved, some of the people that I talked to in my own university said, why on earth are you actually looking at the beetle? It's just evolving into something else, somebody said to me in the biology department. I thought, how sad. He wasn't even interested in finding out how the thing worked. Well, my position, quite unashamedly, is chapter 1 of the book of Romans says, since the creation of the world, his invisible attributes are clearly seen, being understood by the things that are made, even his eternal power and Godhead, so that they are without excuse. Whatever you think about that verse, some of you won't agree with me, but you cannot tell me that having a design position closes down research. My testimony is that I'm a Christian. The greatest thing that Christ has done for me is that he died on the cross for my guilt. He's also given me opportunity to work out some of the secrets of nature. And the glory goes to God, not to me. Thank you, ladies and gentlemen. It's up to my good host to tell me what we're doing.
Yeah, time is short. Is this mic working? Can you hear me?
Turn it on.
That's just my last slide that you might just see.
Let's just
say, this is the brilliant engineer, which of course I'm giving glory to. And can I just say, that book is down there, right? And there is other materials down there, but we've only got 1 or 2 copies of the one on the left, Genesis, for today. And Genesis 1 through 11, we've got quite a few more copies.
Let's just take a minute and stretch. Everybody stretch and just take a minute And Chris Kennard is down here. Raise your hand, Chris. If you'd like to give a gift to help us toward the cost of this program tonight. I apologize about our late start. We're so glad to have you, Andy.
That's great to be here.
All the way from the UK, Scotland.
No, England.
You got a plaid tie on.
Yeah, so that's my clan.
But you're a McIntosh.
Yeah, well, McIntoshes don't just live in Scotland, some of them live over here.
From Leeds, England. We're so glad to have you, and let's just take a minute to stretch and come back, and let's do as science going on. Please stay to the end. We have a very well, dear professor friend of ours, and he's from the other point of view, and he has some questions he'd like to ask. In fact, he shared that he's written a couple articles in response to you, and I want to give him due. But if those of you who would like to ask questions, please save them for the end, and we'll have question and answers. But I'm looking forward to your second lecture.
So we're going to start in 5 minutes? What are you telling me?
Let's take a 2-minute break, because if somebody has to leave, they'll leave now. But let's just take 2 minutes and stretch, and we'll come right back.
Thank you.
Thank you.
Okay.
If you move around.
I got it.
I'll try and make it quicker. John, I'll try and make it as fast as possible. I'll probably skip things.
Careful, careful.